When we have small, and very large equilibrium constants, we can often make approximations that make our calculations easier. Let's see how that works with the following example. A vessel is charged with 1 bar of chlorine gas, and it's allowed to come to equilibrium with atomic chlorine. And we want to know the pressure of chlorine atoms at equilibrium. So, like all equilibrium problems, we're going to start by writing the equilibrium reaction. So we have chlorine in the gas phase. Chlorine is a diatomic molecule, and we're going to have it in equilibrium with chlorine atoms in the gas phase. So we're going to form 2 chlorine atoms. And we know that the equilibrium constant in terms of pressures is 1.3 times 10 to the minus 37. And we want to know what is the pressure of chlorine gas atoms at equilibrium. So we're going to set up this equilibrium problem the same way we always set up equilibrium problems, and we're going to start by saying, what do we have initially in our vessel? The problem says that the vessel is charged with 1 bar of chlorine gas. That means that I charged, I gave it, I started with 1 bar of chlorine, and I didn't put any chlorine atoms in my vessel, and so I have 0 of those to start with. To get to equilibrium, I'm going to have to make some chlorine atoms. And every time I use up a chlorine molecule and it falls apart to form chlorine atoms, I make 2 chlorine atoms. So if I use up X chlorine molecules, I will make 2X chlorine atoms. And then at equilibrium, that means I'm going to have 1 minus X of the chlorine molecules, and I'm going to have 2X of the chlorine atoms. I know that my equilibrium expression for this reaction is the pressure of chlorine atoms squared, because I have 2 of those, divided by the pressure of chlorine molecules. And that is going to be equal to, when I reach equilibrium, that quotient will always be equal to the equilibrium constant value, which is 1.3 times 10 to the minus 37. My ICE chart tells me that the pressure of chlorine molecules is 1 minus X at equilibrium, and the pressure of chlorine atoms is 2X at equilibrium. So I can make those substitutions and write that 2X quantity squared is equal to 1 minus X. Now, at this point, I'm going to think about whether I can make some approximations or not, because I recognize that I'm going to end up with a quadratic equation because of this 2x. And if I could avoid solving the quadratic expression, it would be really nice. So let's think carefully about what it means for an equilibrium constant to be this small, very, very small. That means that the amount of products that I make in this reaction is extremely small. I use up almost none of the chlorine gas and make a very, very small amount of chlorine atoms. And therefore, X is going to be really, really small compared to the 1 bar of chlorine gas that I started with. So if I take 1 and subtract an extremely small number, it will essentially still remain 1. And so I can say that X is very, very small compared to 1 because I have this extremely small equilibrium constant. So if X is very, very small compared to 1, then I can approximate 1 minus X as approximately just equal to 1. And that simplifies my problem because now I have 4x squared divided by 1, or just 4x squared, is equal to my equilibrium constant of 1.3 times 10 to the minus 37. So to solve for x, I just need to divide 1.3 times 10 to the minus 37 by 4 and take the square root to find x. And when I plug that into my calculator, I will find that x is equal to 1.8 times 10 to the minus 19, and that's in units of bar because I have a Kp value, so those are always in terms of bar. So we can see that this X is in fact really, really small compared to 1. If I take 1 and subtract this number from it, I will just have 1. And so essentially, none of the chlorine molecules have decomposed to form chlorine atoms, a very, very small negligible amount. But if I really want to know the pressure of chlorine atoms that I would have in that system, I can calculate it as 1.8 times 10 to the minus 19 bar.